This video was made possible by Skillshare, an online learning community with thousands of classes for anyone who loves learning and wants to explore their creativity and learn new skills. Whether you want to get better at photography, learn how to paint, want to create a really good dessert for your friends, or learn a new language, with Skillshare you will have all of that on one platform. While preparing this video, I listened to the advanced Adobe Premiere tutorial by Jordi van de Put, and thanks to him you can now enjoy subtitles like never before, and my workflow has been improved quite a bit. And now it's your turn. With the link in the description you will get 1 month free trial of ad-free, high quality and never-ending classes, where you can explore your creativity. But only the first 1000 people to click on the link will redeem this offer, so be sure to do it right now. Starting out in astrophotography can be quite difficult. There are a lot of new things to learn, some of them more important than others. But if you have seen backyard astrophotographers taking images like these and want to do the same, there is one step you cannot get around: calibration. This is the first video in a series where I will try to do my best to explain what calibration is, how to do it and what these calibration frames are. You might have heard about bias, dark and flat frames, that they are used to correct something in the image. But what exactly do we need to correct? Join me on this journey. My name is Tim and welcome back to Astro Addict. I'm sitting here with my beloved stacking software, Astropixel processor. I have a couple of images loaded, a dataset from last summer or maybe 2 summers ago, when I photographed the Pinwheel galaxy. As I said, there are I think 44 images loaded here and I already stacked these light frames. The images you take the night of your actual object are called light frames. Deep sky astro images are stacked to reduce noise, because the signal to noise ratio will be very bad in deep sky, so we stack them to make that better. So if we reduce noise by stacking, why do we even need to calibrate them beforehand? Right now I can already see 2 defects in this single exposure which I would like to correct. We have these dark spots. In the case of this telescope they are circles because it was a reflector, a mirror telescope. Dust on the mirrors or any dust in the system will be amplified to such a dark ring. I'd like to remove that. Plus, if I zoom in more closely, right here for example, I will zoom in more, this is a hot pixel, right next to a cold pixel actually. So hot pixels are pixels that don't behave in the way they should. They display or collect way more light than they should, or they just gather these electrons which are considered as light from somewhere. And cold pixels don't receive enough and therefore are blue. And the next thing over here, can you see it in the recording? I will zoom in. On the right hand side you can maybe see some as if light streaks entering the image. And if this exposure would have been any longer, you would have also seen it on this side down here. That's amplifier glow. Most cameras have amplifier glow, even DSLRs, so also a defect which I'd like to remove. We can remove these defects by using calibration frames. After stacking, these imperfections will be way worse. Let me show you what I mean. I have this single test image stacked right here. Yeah, and that doesn't look really good. I mean, the galaxy is in the middle, sure, I could just crop it all the way to the center, but the dust motes would still be there. We can see amplifier glow down here on the left hand side, on the right hand side, dust motes and vignetting, tons of vignetting. You can see that the hot pixels have been slightly removed, but that's not due to stacking, that's due to the software doing its thing. APP is pretty good in that regard. And you can also see a satellite going through here. Sadly there are no calibration frames for satellites. But these are the defects we need to remove if you want to get a good image. In order to better understand how to use these calibration frames and for which type of error we use what frame, let's first look at the telescope, at the entire rig, where these errors come from. These types of errors all originate from somewhere in the optical train. And the fact that we are stacking many images will only make these imperfections worse. These imperfections, hot pixels, vignetting, dust, will be corrected if we use calibration frames. But first, we have to learn where these imperfections come from. Here we have the optical train. Vignetting and uneven illumination originate from the lenses, while dust can sit along the entire path from first lens to camera sensor. The corresponding calibration frame is called a flat frame and will be subject of a later video. Hot and cold pixels as well as amplifier glow originate from the camera and are attacked by dark frames. Again, the topic of a later video. In this video I will focus on readout noise, which originates from the camera. A bias frame is used to correct for readout noise in your final image. Readout noise appears in every exposure you take, regardless of exposure time or other settings. At the end of the exposure, when the literal electrons, which are saved inside the sensor, are flushed out to the processing unit, they are flushed out with more electrons. And these extra electrons constitute the readout noise. But before we can remove this noise from our image, let's first take a couple of bias frames. I will now use this DSLR to take an image of only the readout noise. To do this, no light can enter the camera, and I will not introduce any other type of dark noise by using the fastest shutter speed this camera can do. And that's it. So now let's take a look at that. Right here I imported bias frames into APP. I have a couple of different ones because I want to show you different results with different bias frames, let's say. Right here, a single bias frame, ISO 400. So if I zoom in, this looks pretty much random. We have noise, of course, but maybe you can see in the recording some streaks, some banding, horizontal and vertical. And if we now stack multiple of these bias frames, we will start to see some regularities. I imported 3x20 bias frames, ISO 400, ISO 1600 and ISO 1600 with a special treatment. So I will now stack these bias frames into 3 master bias frames. So let's take a look at the first one. ISO 420 bias frames. Did you ever wonder where banding noise comes from? I think I found the answer. Zooming in we see banding, who would have guessed? So that's the first type of noise that the bias frame is used to reduce, to subtract, to get rid of. And one more thing, if I go to the up here, you will see this strange line of darker pixels. Thinking back to my image processing classes when we discussed sensors and how they save images, I think this is the line where all the electrons are flushed out. So all the electrons when saved are pushed up here and then to the left, because up here is 0, 0, the origin. I believe that's the reason why this line looks much more different than the others. In typical astrophotography, this line would be cut out anyways. We usually crop our images, crop the edges to get rid of stacking artifacts. Yeah, that's also in your image, in every type of image. May it be a DSLR or dedicated astronomy camera, bias noise will be there and you should remove it. Let's quickly take a look at a 1600 bias frame. So this actually looks different. Maybe it's just a different stretching that APP has applied, but we can still see basically the same. The next frame is a bias frame stacked 20 frames, ISO 1600. But I put the camera in the fridge for 20 minutes. And as you can see, there is not much difference. And that's the point I will explain later. Every stacking software will do that job for you. All we have to do is to take and load the bias frames. But how do we actually take them? Good news, that's the simplest part. Take your camera and set it to the fastest shutter speed it can manage. For most DSLRs that will be 1/4000. And the temperature does not have to be the same as in the light frames. But, and this is very important, Bias frames are ISO dependent. You have to take them with the same ISO than your light frames you took in the night. And since we need to stack our bias frames, take at least 20 of them to get a good result. The bias frame is used to correct for readout noise in your image. To take these correction frames, use the fastest shutter speed your camera can do, put the cap on, and use the same ISO as in your light frames from the previous night. You can of course take them in the same night. The temperature does not matter. And to get a good result, take at least 20 bias frames to be stacked into a master bias. Taking less than 20 can actually harm your image. The last topic I want to tackle today is the discussion about dark flat frames. This is for more advanced astrophotographers who use dedicated astronomy cameras. Many people and even some manufacturers do not recommend the usage of bias frames. Instead, they use something called a dark flat frame. Since this series is for beginners, you don't need to worry about that yet, especially if you use a DSLR. I will talk more about these dark flat frames in the upcoming video about flat frames. If you have any questions, as always, feel free to leave them in the comments down below. I will see you in the next part where I talk about dark frames. And as for me, my name is Tim, I'm an astro addict. I wish you clear skies and may the night be with us.